Hello, welcome to another tutorial with Ford Academy. In this video, I will be discussing about the ordinary least squares regression, its assumptions, limitations, ways to address its limitations, and alternatives to OLS. So, let's dive right in. Ordinary least squares regression is a statistical method used to estimate the relationship between a dependent variable and one or more independent variables. The main goal of OLS regression is to find the best fitting straight line through a set of data points. This line helps you understand the relationship between a dependent variable and one or more independent variables. Y represents the dependent variable and xi represents the explanatory variables. We could always have multiple explanatory variables, which is also known as independent variables. So we could always have multiple independent variables. OLS assumes that the relationship between the dependent variable and the independent variables is linear, which implies that the change in dependent variable is consistent with the change in the independent variable. OLS finds the equation for the straight line that minimizes the total square difference between the actual values of the dependent variable and the predicted values by the equation. These differences are either called residuals or errors. Here is the general model for the least squares regression, where y represents the dependent variable, beta naught, beta 1 down to beta p represents the coefficient of the independent variables, x1 down to xp represents the independent variables, and ei represents the error term. The graph shown is a simple graph fitted for the OLS regression. The difference between the dotted point and the straight line fitted represents the errors or the residuals. Assumptions of OLS regression. Linearity. OLS assumes that the relationship between the independent variables and the dependent variable is linear. This means that there is a straight line trend in your data. Normality. For hypothesis testing and constructing confidence intervals, OLS assumes that the residuals are normally distributed. Homoscedasticity. The residuals have constant variance across all levels of the independent variables. OLS assumes that the residuals are independent. The differences between the actual and predicted values should not be related to each other. They should be independent observations. Limitations of ordinary least squares regression. While ordinary least squares regression is widely used, it also has its limitations, and it is very important to note the several limitations of the OLS regression in order to avoid incorrect conclusions. Linearity. The assumption of linearity limits the application of OLS to specific datasets. If the true relationship in a dataset is nonlinear, OLS may not provide an adequate fit, leading to a biased estimate and poor prediction. Normality. Due to its assumption of normality, non-normality can affect the reliability of hypothesis tests and confidence intervals, particularly in small samples. Overfitting and underfitting, including too many predictors relative to the number of observations, can lead to overfitting, where the model captures the noise in the data rather than the true underlying pattern. Likewise, including too few predictors can miss important relationships in the data, which results in poor generalization. Multicollinearity. When independent variables are highly correlated with each other, it becomes difficult to isolate the individual effect of each predictor on the dependent variable. This can lead to large standard errors for the coefficients, making it difficult to determine their significance. Homoscedasticity. OLS assumes that the variance of the residuals is constant across all levels of the independent variables. Hence, if the variance of the residuals changes, it can lead to inefficient estimates and affect the validity of hypothesis tests. Sensitivity to outliers. OLS is sensitive to outliers, which can excessively affect the estimated coefficients. Outliers can distort the regression line and lead to misleading results. Addressing the limitations of ordinary least squares regression. Several corrective measures can be applied to significantly enhance the reliability and validity of the conclusions drawn from OLS regression models. These corrective measures include transformation of variables, making use of alternative regression techniques, making use of time series and spatial models, making use of cross-validation techniques, and analyzing residual plots. So we'll be discussing these several corrective measures one after the other. Transformation of variables. For nonlinear relationships, transforming the variables into other forms such as log, square roots, and so on can sometimes linearize the relationship. Alternative techniques like ridge regression, lasso regression, or robust regression can handle multicollinearity and outliers better than OLS. Therefore, it is important to opt for either of these options whenever there is multicollinearity or outliers in order to avoid biased results. Making use of time series and spatial models. For specialized models like ARIMA, it is much more appropriate to opt for specialized models like ARIMA for time series or spatial regression models for data with autocorrelation. Using cross-validation techniques can help prevent overfitting and provide a better estimate of the model's performance on new data. Analyze residual plots. Regularly checking residual plots can help diagnose heteroscedasticity, autocorrelation, and non-normality. Alternatives to ordinary least squares regression. There are several alternatives to the OLS regression model. And because there are several alternatives, it is very important to understand the alternatives to OLS and their appropriate usage in order to choose the most suitable method for your statistical analysis. For data sets with multicollinearity, an alternative to OLS includes principal component regression, lasso regression, partial least squares regression, and ridge regression. For a data set that is nonlinear, an alternative includes polynomial regression, nonlinear regression, and decision trees. And for data sets that are non-normal, an alternative is the generalized linear model. And lastly, for data sets with outliers, an alternative to that is a robust regression model. Thank you for watching.